A powerful infrared observatory is essential in our quest to observe the initial formation of stars and galaxies in the universe. What is the purpose of observing the initial stars and galaxies that emerged? One explanation is that it is still necessary. Approximately 380,000 years after the Big Bang, the microwave COBE and WMAP satellites detected the residual heat signature it produced. However, at that particular juncture, the presence of stars and galaxies was non-existent. Indeed, the universe was devoid of light. Following the Big Bang, the universe existed in a state resembling a highly heated mixture of particles, specifically protons, neutrons, and electrons. As the universe was cooling, protons and neutrons started to merge, forming ionized hydrogen atoms and some helium. The presence of ionized hydrogen and helium atoms caused electrons to attract, converting them into neutral atoms. This phenomenon allowed light to propagate without dispersing by free electrons for the first time. The universe has become transparent. Nevertheless, it would take a considerable amount of time, potentially several hundred million years after the Big Bang, for the initial light sources to emerge and end the period of cosmic darkness. The appearance of the universe's initial light, which resulted from the fusion of hydrogen atoms into helium by the first stars, remains uncertain. Similarly, we still need to discover the precise timing of the formation of these early stars. Imagine the light emission from the initial stars and galaxies some 13.6 billion years ago, traversing space and time to ultimately reach our telescopes. We observe these objects as they appeared 13.6 billion years ago, when light from them first reached us. When the light reaches humans, it changes color or wavelength towards the red end of the spectrum, known as a redshift. For what reason? This is because Einstein's theory of general relativity becomes relevant when discussing objects that are far away. It informs us that as the universe expands, the interstellar space between objects stretches, resulting in moving objects, galaxies, away from each other. Furthermore, any light in that area will undergo stretching, causing its wavelength to increase and shift towards longer wavelengths. This phenomenon can make distant objects appear significantly faint or imperceptible when observed using visible wavelengths of light, as they emit infrared light that reaches us. The Webb telescope can observe events that occurred about 100 million to 250 million years after the Big Bang. However, to understand the early cosmos, we must perceive infrared light. These objects cause the wavelength of light to shift towards the red end of the spectrum. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, is crucial in comprehending the early universe. At extremely distant redshifts, the visible light often shifts towards the electromagnetic spectrum's near and mid-infrared regions. At extremely high redshifts, or when observing the most distant objects, visible light typically transitions into the electromagnetic spectrum's near and mid-infrared regions. Therefore, Webb's design requires a robust near- and mid-infrared telescope to observe the initial stars and galaxies. Webb poses a series of crucial inquiries that help us understand the creation of structures in the cosmos. These questions serve as a guide to unraveling the tale behind their construction. What were the specific times and processes of reionization? Which sources were responsible for the reionization process? What are the most ancient galaxies? The Webb telescope will conduct extensive surveys of the universe using near-infrared technology to locate the initial galaxies. It will then use low-resolution spectroscopy and mid-infrared photometry to determine the electromagnetic radiation intensity of these celestial objects. To investigate reionization, it is necessary to utilize high-resolution near-infrared spectroscopy. The universe remained in a state of profound darkness for several hundred million years following the Big Bang. Stars and galaxies were completely absent. Following the Big Bang, the universe existed in a state resembling a highly heated mixture of particles, specifically protons, neutrons, and electrons. During universal cooling, the protons and neutrons commence the amalgamation process, forming hydrogen and deuterium ionized atoms. Deuterium undergoes further fusion to become helium-4. The presence of ionized hydrogen and helium atoms resulted in electron attraction, causing their conversion into neutral atoms. The universe consisted of 3 times as much hydrogen as helium, along with small quantities of other lightweight elements. The phenomenon of particle aggregation, referred to as recombination, occurred around 240,000 to 300,000 years after the Big Bang. It represented a notable shift in the cosmos from opaque to transparent. In the past, free electrons frequently underwent scattering due to their interaction with light, impeding their unrestricted propagation. By forming bonds with protons, unbound electrons eliminated any obstacles to light. The era of recombination refers to the earliest period in our cosmic history that we can observe using any light. Satellites like the Cosmic Microwave Background Explorer, COBE, and the Wilkinson Microwave Anisotropy Probe, WMAP, currently observe the cosmic microwave background. After this, cosmic dark ages occur, denoting the interval between the universe's transition to transparency and the emergence of the initial stars. The formation of the first stars marked the end of the dark ages and the beginning of the next era in our universe. Following the formation of the initial stars, alterations occurred. According to theoretical predictions, the initial stars were significantly larger than our Sun, ranging from 30 to 300 times its mass. These stars were also much brighter, with millions of times greater luminosities. However, their lifespan was very short, lasting only a few million years before undergoing supernova explosions. These initial stars emit intense UV radiation that can dissociate hydrogen atoms into electrons and protons, thereby ionizing them. The period referred to as the Epoch of Reionization spans from the conclusion of the Dark Ages to when the cosmos reached approximately 1 billion years of age. During this period, the increasing radiation emissions from the initial colossal stars caused the reionization of most neutral hydrogen. A reionization is a significant event in our universe's history because it provides us with a limited opportunity to study the earliest stars through indirect means. Scientists require precise knowledge of the exact timing of the first star's formation and the reionization process's commencement. The emergence of these initial stars marks the end of the Dark Ages in the cosmic timeline, a period characterized by the absence of distinct light sources. Understanding these first sources is a scientific endeavor and an exploration of our cosmos's astonishing origins. The initial illumination sources serve as catalysts for the subsequent development of larger entities. The Hubble Space Telescope is well known for its astronomical observations in the Hubble Deep Field. This is the first significant retrospective examination of the early formation of galaxies in the history of the cosmos. A long exposure technique captures a small portion of the sky, revealing numerous dim objects previously invisible. According to Stefano Cristiani, these objects are among the most ancient and remote galaxies, giving us a glimpse into the initial stages of galaxy creation around 10 billion years ago. We will then undertake more extensive investigations and conduct deep field experiments with Webb. Webb's advanced imaging capabilities and infrared vision will provide unparalleled clarity when observing the early universe. Furthermore, it is possible that the initial stars that underwent supernova explosions later collapsed, forming black holes. The black holes initiated the process of engulfing gas and other stars, forming mini-quasars. Subsequently, these mini-quasars developed and combined to become the colossal black holes currently observed at the cores of almost all major galaxies. During the early stages of the universe's development, hydrogen atoms emitted several bursts of light, all occurring at a consistent wavelength around half the height of a bowling pin. After an extremely long period of time, the expanding universe stretched the photons to different lengths. Eventually, some of these photons reached Canada, where a specialized radio telescope was ready to capture them. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, is a highly ambitious cosmic instrument. The researchers developed CHIME to elucidate dark energy, the force responsible for the universe's expansion, by producing a comprehensive map of a hitherto inaccessible period of time. This window is not observable through alternative means, stated Kiyoshi Masui, an astronomer at the Massachusetts Institute of Technology. We are pursuing an inaccessible period. CHIME can potentially solve a significant modern astronomical puzzle, the source of fast radio bursts, FRBs, explosive events occurring outside of our galaxy. While driving through the dry foothills of southern British Columbia, drivers may notice signs requesting them to turn off their telephones as they approach the Dominion Radio Astrophysical Observatory, where CHIME and other scientific instruments are located. When intercepting photons emitted from distant regions of the universe, it is imperative to maintain absolute silence. The CHIME radio telescope employs 4 half-pipe-shaped ears that collectively cover an area equivalent to the length of a football pitch and half its width. Oriented vertically, the receivers span a significant portion of the celestial dome and rely on Earth's motion to navigate the cosmos. The mechanical simplicity of this device masks a highly intricate digital sophistication. CHIME is unique among radio telescopes due to its impressive array of 1,000 antennas. Interferometry, a computationally intensive technique, compares the signal from each antenna with that of every other antenna to create an image. CHIME's true strength resides in its many processors, which effectively diminish the overwhelming influx of data to a more manageable flow of approximately 1 terabit daily. "We have substituted mechanical expenses with digital expenses," Masui said on space.com, resulting in a highly cost-effective telescope. In 2012, the Canadian government allocated approximately 12 million Canadian dollars, $9 million to finance the interferometer, which was considered a cost-effective investment in astronomy. Masui claims that the payment made it possible to acquire an instrument that could map 10 to 100 times faster than any other. CHIME possesses great resolution, a wide panoramic field of vision, and exceptional low-light capabilities. However, it would be considered an optimal camera if it could detect visible light instead of operating within the frequency range of 400 to 800 MHz radio waves. The fully assembled telescope commenced its initial measurements in September 2017, and rigorous testing persisted throughout 2018. The equipment commenced full operation in early 2019 and will ultimately conduct continuous observations of the celestial sphere. The main goal of CHIME is to cartographically depict the observable substance of the universe on a large scale and gain insights into the forces that propel it. Instead of mapping specific galaxies, the equipment merely detects the most prevalent constituent of the universe: hydrogen. Despite its modest size, due to its widespread occurrence, the hydrogen atom is considered a suitable representative for all ordinary stuff, including stars, galaxies, and galaxy clusters. The tiniest constituents that are observable to us correspond to hundreds of thousands of galaxies, stated Richard Shaw, a cosmologist at the University of British Columbia in Vancouver, Canada. The neighbouring dull galaxy appears as a luminous cluster from a distance. Therefore, CHIME will utilise a cosmic anomaly to enhance the depth of its map. The cosmos originated as a dense and viscous plasma filled with undulations. Over 300,000 years, this mixture underwent cooling, leading to the formation of hydrogen atoms and the preservation of the first vibrations. CHIME will search for the remaining mass concentrations, manifested as vast rings of galaxies and hydrogen spanning around 1 billion light-years. Scientists will create the most extensive image of the universe ever made by merging the development of these ancient halos with data on the degree to which photons stretch throughout their journey to Earth. This map will reveal the speed and timing of the cosmos's expansion. The primary objective is to get statistical data to eliminate certain dark energy hypotheses. As a result, the experiment specifically investigates hydrogen atoms that showed intermittent flashes between 2.6 billion and 6.8 billion years after the Big Bang. That's when dark energy initially gained significance, Masui stated, at its inception when the universe's expansion diverged from our anticipated trajectory. CHIME's observations will eliminate not only dark matter models, but also other hypotheses. The interferometer can detect transient cosmic bursts even during the initial phases of telescope development. Researchers first observed the first fast radio burst, FRB, in 2007, but it took several years to reach a consensus that the extraordinarily luminous radio bursts did not originate from Earth. Astronomers have documented numerous instances of these bursts, which rapidly alternate between being visible and invisible within fractions of a second. Flashes dotted the sky, occurring numerous times daily and originating from various locations in the universe. However, the trigger for these flashes remains unidentified. In 2014, the Canadian Institute for Advanced Research held its annual conference on cosmology and gravity in Quebec shortly after CHIME secured funding. The researchers recognized that CHIME's capacity to simultaneously scan the sky would be well suited for identifying widespread and unpredictable radio bursts. 2 years later, the government allocated a substantial amount of CA6 million, 4.5 million, to establish a computing cluster that would promptly analyze CHIME's data for fast radio bursts, FRBs. It was a remarkable achievement in Canadian radio astronomy, Masui stated. Before its full activation, the telescope significantly altered the fast radio burst, FRB, research landscape. At the beginning of 2019, the partnership released 13 new findings, which included the discovery of a second instance of a repeating burst. These findings, known as fast radio bursts, FRBs, were observed emanating from the same location. As a result, the number of known FRB occurrences increased by 25%. CHIME saw the flashes for 4 weeks, but after accounting for time spent on debugging and calibration, Masui estimates that the telescope was completely functional for only 5 days. Recent discoveries, particularly the recurrent burst, have already assisted astronomers in refining certain hypotheses. However, researchers will require several further observations to pinpoint a definitive explanation for fast radio bursts, FRBs. The initial 200 or 1,000 examples will eliminate a significant number of models, stated Masui. However, numerous models exhibit excellent performance. Even if you eliminate 75% of them, there will still be a significant number that function effectively. In 1929, an American astronomer, Edwin Hubble, made the groundbreaking observation that the distances between galaxies far away from us were directly proportionate to the redshifts they exhibited. As a light source moves away from its viewer, the Doppler effect causes a redshift, stretching its apparent wavelength towards the red section of the spectrum. Hubble's findings indicated that distant galaxies were receding from us, as the galaxies farthest away exhibited the highest apparent velocities. Hubble deduced that if galaxies are receding from us, they must have congregated closely at some juncture. Hubble's discovery provided the first empirical evidence for Georges Lemaitre's 1927 Big Bang theory of the universe. Lemaitre postulated that the cosmos originated in a highly compact and heated condition and is presently undergoing expansion. Subsequent calculations have determined that the Big Bang occurred approximately 13.7 billion years ago. In 1998, 2 groups of astronomers conducting separate research in Berkeley, California, observed that supernovae, which are stars that explode, were exhibiting an increasing velocity as they moved away from Earth. They received the Nobel Prize in Physics in 2011 as a result. Physicists previously hypothesized that the expansion rate of matter in the cosmos would gradually decrease over time, as gravity would eventually exert enough force to cause the universe to contract towards its center. While the Big Bang theory cannot explain the initial conditions of the universe, it does assist physicists in describing the early stages following the expansion. Immediately following the Big Bang, the universe was characterized by intense heat and high density. The universe's temperature decreased, forming quarks and electrons, which are matter's fundamental constituents. Shortly after, quarks combined to form protons and neutrons. In minutes, these protons and neutrons merged to form nuclei. As the universe underwent expansion and cooling, the rate of events gradually decreased. Capturing electrons in stable orbits around nuclei took 380,000 years, leading to the formation of the initial atoms. Primarily, the universe consists of helium and hydrogen, the 2 most prevalent elements. Current evidence indicates that the initial stars emerged from gas clouds approximately 150–200 million years following the Big Bang. Subsequently, stars have consistently generated more massive elements such as carbon, oxygen, and iron, propelling them across the cosmos through extraordinary stellar explosions called supernovae. However, a complete narrative requires more than just stars and galaxies. According to astronomical and physical estimates, the visible cosmos accounts for only 4% of the universe's total composition. An unidentified form of a substance known as dark matter makes up a substantial fraction, precisely 26% of the cosmos. Dark matter, in contrast to stars and galaxies, cannot generate light or electromagnetic radiation. Therefore, its detection is solely reliant on observing its gravitational influences. Dark energy, a highly enigmatic energy, constitutes approximately 70% of the total mass energy in the cosmos. It's more obscure than dark matter. This concept originates from the observation that all galaxies appear to be moving away from one another at an increasing rate, suggesting the presence of an unseen additional energy. Scientists have found mysterious substances in space, and they theorize that these substances have sparked cosmic-scale chemical reactions. The initial constituents of the universe were not actual atoms, but rather nuclei that had not yet acquired electrons. The most basic nucleus, such as that of hydrogen, consists solely of a proton without any further features. During the moment of the universe's creation, energy was abundant. There was a collision between many objects. Protons and neutrons frequently have collisions, resulting in the formation of bigger nuclei. Examples are deuterium, which consists of a proton and a neutron, and helium nuclei, which consist of 2 protons and 2 neutrons. Additionally, other alternative configurations of protons and neutrons emerged. However, these alternate combinations were variations of hydrogen, helium, and small amounts of lithium, as the number of protons in an atom determines its identity. Helium was the initial element among these 3 to develop genuine atoms. An atom consists of a nucleus and electrons. Helium nuclei were the first to accumulate many electrons collectively. What are the reasons for not considering hydrogen or lithium as alternatives? Helium is the initial noble gas on the periodic table, the first atom possessing sufficient electrons to occupy all the accessible positions in its electron shell. Therefore, helium is the most efficient element in acquiring and manipulating electrons within the periodic table, using electrons as the fundamental units of chemical interactions. Stealing 1 electron from helium requires more energy than any other element in a contemporary laboratory setting. The energy required to ionize a second electron is more than double that required for the initial ionization. During the early stages of the cosmos, helium nuclei rapidly acquired electrons and filled their electron clouds before hydrogen nuclei could do the same. Additionally, there were enough lithium nuclei to gather all 3 necessary electrons. During that period, most matter in the universe consisted of solitary protons that lacked an electron. They began decelerating and actively seeking partners with opposite charges to achieve electrical neutrality. However, capturing free electrons proved to be challenging for the protons. As a result, they resorted to combining with helium, which already possessed some electrons. Despite its reluctance to bond, helium often encounters persistent hydrogen nuclei. Eventually, the collisional pressure caused several helium atoms to share electrons with protons. This led to the formation of the first chemical bonds. The chemical formed by combining helium and hydrogen, known as helium hydride, H+, is considered the first molecule in the cosmos to exist in significant quantities. Because it was the least inclined element to engage in chemical reactions, helium was the initial element that formed chemical bonds. This is because helium is a noble gas with a complete set of electrons, making it content and uninterested in bonding with other elements. Nevertheless, helium was the only element present in the early universe, and electrons were accessible for borrowing. Although theoretical foundations have firmly supported this narrative for many years, it still requires empirical evidence to confirm its validity. Only on Earth can laboratories synthesize H+, leaving its presence in space unnoticed for several decades. Recently, astronomers made a groundbreaking discovery by detecting this chemical for the first time in the remnants of a dying star. The effort finally paid off after 4 decades of searching, adding a significant and essential component to our understanding of the genesis of the early cosmos. Scientists have identified H+ as one of the many chemicals found in space, discovering over 200 different molecular species. Astrochemistry, commonly referred to as the study of chemistry beyond Earth, aims to clarify the composition of molecules in space, comprehend their formation mechanisms, and investigate the implications of their evolution for observational and theoretical astrophysics. Several well-known macromolecules, such as water, ammonia, and formaldehyde, are abundant on Earth. Other substances exhibit this peculiarity, such as hydrochloric acid with an additional proton and hydrogen peroxide with one of its hydrogen atoms removed. In addition, we have detected ions, systems with unpaired electrons, and unconventional atomic configurations within ordinarily typical molecules. We have observed molecules that include chemically unreactive noble gases, such as Arch+, a combination of argon and hydrogen, and the recently discovered H+. Most branches of chemistry's primary goal is to improve human safety, efficiency, or enjoyment of the world. Astrochemistry, on the other hand, examines the fundamental characteristics of molecules. It helps clarify bonding, molecular integrity duration, and specific chemical species prevalence. By exploring chemistry in extreme environments with unconventional conditions, such as non-Earth-like temperatures, pressures, and components, we can discover compounds that defy our conventional understanding of atomic interactions and enhance our knowledge of chemistry. Ultimately, our objective is to understand the role of chemistry in the formation of the elements present on the planets inside our solar system, which ultimately facilitated the emergence of life. Where was the HEH+ ion located? T conducted experiments at a laboratory at the University of California, Berkeley, in 1925. R. Hogness, who later contributed to the Manhattan Project and taught fellow E.G. Lunn, observed that the combination of helium and hydrogen gas when subjected to an electric arc in a vacuum chamber could generate several ions with distinct masses. Mass spectrometry is a scientific field that specializes in determining the ratio of mass to charge of molecules. Researchers discovered that this mixture temporarily created a mass-to-charge ratio of 5 during its initial application. The only possible ion is HeH+. Nevertheless, preserving this noble gas molecule for an extended period to conduct research posed a considerable challenge, even inside the controlled laboratory environment of Hogness and Lunn. H+'s propensity to readily release its proton at even the smallest interaction with another atom would have exacerbated its instability in the early universe. Helium donates a pair of electrons in this interaction, but hydrogen does not donate any. Asymmetric dative bonding is weaker than conventional covalent bonds, where both atoms participate more equally. In 1978, John H. Black, affiliated with the University of Minnesota at the time, was the first to propose the potential existence of HeH+ in outer space. Black proposed that planetary nebulae were a promising location to search for the expanded and highly energetic material formed during the last stages of a star's life. Within these clouds, neutral hydrogen atoms typically contain a tiny layer of ionized helium atoms. Helium's high affinity for electrons may induce it to acquire one from hydrogen, forming a bond. Therefore, since the late 1970s, astronomers and their chemist partners have been searching for HeH+ in various locations, ranging from the furthest regions of the universe to extremely large stars. However, these searches have been unsuccessful for many years, causing skepticism regarding the credibility of HeH+'s contribution to initiating chemistry. Did helium form a chemical bond with a hydrogen ion, H+? At the time, it was the only option for connection, as there were no other alternatives. However, if it were true, the question would arise: where was the HeH+ ion? Although astrochemists were unsuccessful in their hunt for HeH+, they did make numerous unexpected discoveries of other substances, several of which remained unidentified. In 1919, Mary Lee Heeger utilized the Lick Observatory, situated atop Mount Hamilton in Santa Clara County, California, to study the actions of a pair of binary stars in orbit, resembling the twin suns of Tatooine. The sight that she witnessed was astonishing. Every molecule possesses a distinct configuration of atoms and electrons, allowing it to absorb light selectively. The absorption features are distinct characteristics unique to each molecule. Astronomers can observe these properties using spectroscopy, which involves separating incoming light into its individual wavelengths. While Heger's binary stars revolved around their common center of gravity, the spectral characteristics in each star's atmosphere underwent a wavelength change known as the Doppler effect. However, Heger also identified certain spectral patterns that remained constant while the stars were in motion. Subsequently, she directed her gaze toward another binary star system and observed an identical configuration. Subsequent investigations revealed that these stationary characteristics also manifested when telescopes were directed toward individual stars. The fingerprints likely originated from molecules in the expansive and frigid interstellar regions rather than in the vicinity of stars. We found remarkably identical fingerprints across all visible stars and galaxies. The signatures, known as diffuse interstellar bands, DBs, were present ubiquitously. Scientists extensively studied the recorded characteristics of molecules on Earth, newly created ones in laboratories, and those detected in space using radio telescopes to identify them. The DIBs did not correspond to anything. They were something unprecedented. Prominent astrochemist and former Harvard University professor William Klemperer proposed that the trisulfur anion S3 could be the source of the distinct signatures known as DIBs. Upon discovering the claim's falsehood, he became extremely disheartened and expressed his disappointment by stating, "Speculating about the carriers of the diffuse interstellar bands is the surest path to tarnishing one's scientific reputation." Various theories regarding the origin of the DIBs circulated over the years, but none gained widespread acceptance, making it the most enduring challenge in spectroscopy. PAAs are a potential candidate for the mysterious phenomenon of diffuse interstellar bands, DIBs. Polycyclic aromatic hydrocarbons, PAHs, which consist of carbon atoms arranged in hexagonal structures, are the primary constituents of substances such as soot, asphalt, and graphite. They have a low reactivity to other molecules but tend to adhere to them. The similarity of the many types of patches, which causes their spectroscopic fingerprints or spectra to overlap, is a challenge astrochemists face. Attempting to distinguish the individual brushstrokes in Vincent van Gogh's Starry Night is comparable to trying to perceive the entirety of the painting, as the various elements blend together to form a unified whole. However, the DIBs exhibited comparable behavior. Can polycyclic aromatic hydrocarbons, PAHs, explain the diffuse interstellar bands, DIBs? Astrochemistry communities have discussed these concepts since the 1970s, but one particular experiment has permanently altered our understanding of carbon. Harry Kroto, who passed away in 2016, was affiliated with the University of Sussex in England during the 1980s. He actively contributed to a research team that identified novel chemicals in outer space. Robert F. Curl and Richard E. Smalley, chemists at Rice University at the time, performed an experiment in which they removed material from an aluminum surface and found several different aluminum molecular clusters. Replacing graphite with aluminum led to the emergence of a peculiar molecule known as C60, which consisted of 60 carbon atoms organized like a soccer ball. Kroto, Curl, and Smalley were awarded the Nobel Prize in Chemistry in 1996 for their groundbreaking identification of Buckminster fullerene, sometimes called fullerene or a buckyball. Kroto firmly believed that buckyballs existed in outer space and were highly probable to be responsible for certain DIB fingerprints. Nevertheless, a handful of individuals trusted him, prompting him and his associates to proceed further. In 2010, scientists detected C60 and its relative C70 in the infrared spectrum within the planetary nebula TC1 in the Cygnus constellation, 25 years after their original discovery in the laboratory. The relationship between these compounds and visible wavelength DBs remained uncertain. Theoretical research proposed this hypothesis, but scientists required more validation of the empirical evidence. In 2015, scientists successfully confined the cationic version of fullerene, C60+, within a laboratory setting, enabling them to accurately determine its near-infrared spectrum. Two specific wavelengths from this molecule corresponded to known diffuse interstellar band, DIB, frequencies. Subsequently, researchers demonstrated that these fingerprints corresponded to 4 or 5 diffuse interstellar bands, DIBs. In 2019, Martin A. Cordiner, from NASA's Goddard Space Flight Center, headed an international team that utilized the Hubble Space Telescope to analyze the wavelengths of diffuse interstellar bands, DIBs, observed towards 11 predominantly red, older and larger stars. The team found that these wavelengths aligned with the experimental results for C60+, indicating that the distinctive features of this molecule are responsible for some DIBs. This study demonstrates definitive evidence of a certain type of molecule that leaves distinct marks throughout interstellar space. Scientists believe that polycyclic aromatic hydrocarbons, PAHs, are the origin of buckyballs, and their presence in space implies the existence of the precursor molecules that form them in the cosmos. However, it was only in 2018 that scientists could detect the distinctive characteristics of a molecule belonging to the PAH family in outer space, benzonitrile, C6H5CN. The chemical that was seen is a rare aromatic hydrocarbon that is easier to find than similar compounds. Furthermore, scientists have recently detected double-ring cyanonaphthalene molecules, providing evidence of bigger polycyclic aromatic hydrocarbons, PAHs. Despite these significant advancements, the discovery of HH+ remained difficult to achieve for an extended period. Following the initial epochs, the molecules would have dispersed rapidly. As the cosmos progressed, grew in size, and decreased temperature, the remaining hydrogen nuclei started attracting their own electrons. We can infer that these now uncharged hydrogen atoms likely sensed the positive charge on the HH+ molecules. The atoms and molecules collided and broke the weak He-H dative link. Afterward, the collision of the atoms and molecules created a significantly stronger covalent bond between two hydrogens, creating H2+. Subsequently, the helium atoms remained mostly unchanged. The transient nature of He-H+ may give the impression of insignificance. However, this needs to be more accurate. According to the models, if He-H+ generation had not occurred, the combination of H2+ and neutral H2 would have occurred significantly slower throughout this period. Nevertheless, following the formation of H2, the complete hierarchy of chemistry commenced to unravel. Following H3+, the subsequent result was the formation of CH+, CH2+, and various other molecules. Ultimately, this sequence resulted in water, ethanol, and bigger organisms forming. An imbalance in bonding within He-H+ drives these processes. Without this initial connection, the universe would undergo fundamental alteration. Nevertheless, by 2013, astrochemists were becoming more frustrated by the absence of He-H+. Nevertheless, in that particular year, researchers made an encouraging discovery when they detected the RH+ molecule, a noble gas, in the remnants of the Crab Nebula supernova. In their quest for He-H+, scientists focused on comparable, highly energized environments. The primary issue was that the spectra of He-H+ coincided with the characteristic patterns of the initial molecule detected in outer space, namely, the CH radical. None of the telescopes can distinguish these distinct patterns. Later, NASA introduced the Stratospheric Observatory for Infrared Astronomy, SOFIA, modifying a 747 jumbo airplane by creating an aperture on its side to accommodate an infrared telescope. In May 2016, scientists from several countries utilized SOFIA, a collaborative endeavor between NASA and the German Aerospace Center, for 3 consecutive nights to conduct observations. The SOFIA scope's resolution is sufficient to distinguish He-H+'s distinctive rotational frequency fingerprint at 2010.184 GHz. We discovered a missing fingerprint in the far infrared data of a burned-out cinder from an exploded star within the planetary nebula NGC 7227, located in the constellation Cygnus. This infernal location, characterized by its extreme temperatures and intense energies, closely resembles the primordial cosmos. Rolf Gusten, a researcher from the Max Planck Institute for Radio Astronomy in Bonn, Germany, headed a team that released a study in the scientific journal Nature on April 17, 2019, announcing the groundbreaking discovery of HeH+. Indeed, this observation does not indicate the presence of primordial HeH+. We believe that the compounds Guston and his colleagues observed have a more recent origin. However, the discovery contributes to limiting our comprehension of this chemical. Scientists may create more advanced universe models based on when HeH+ was the dominant chemical. The discovery may provide insights into the potential presence of this chemical in other areas of space, such as planetary nebulae or distant regions that correlate to previous epochs of time, maybe reaching the edge of the cosmos. Astrochemistry is experiencing a period of great excitement. Scientists have promptly resolved 3 important inquiries with definitive responses. They have witnessed the initial formation of the first molecule in the universe, found the initial unique characteristics of the enigmatic dibs, and are currently unraveling the nature of powers in the vastness of space. Laboratory models of interstellar phenomena also demonstrate the potential formation of amino acids and nucleobases. In conjunction with space observatories like SOFIA and Hubble, the upcoming James Webb Space Telescope will provide unparalleled spectrum analysis of celestial objects, potentially revealing novel and less common molecular signatures. Having resolved these identified issues, new dilemmas are emerging. In due course, astrochemists want to address more challenging inquiries, such as, what are the remaining diffuse interstellar bands, DIBs? What are the molecular foundations of life? And what specific chemical composition is required for creating terrestrial planets as opposed to gas giants? The formation of visible stuff in the cosmos results from electron sharing. By acquiring a more profound comprehension of these chemical processes, we can attain a more detailed understanding of astrophysics and the comprehensive history of our universe. The cosmic microwave background, CMB, refers to the residual radiation that originated from the initial explosion of the cosmos, commonly known as the Big Bang. According to the idea, the cosmos experienced a period of fast inflation, expansion, and cooling after its birth. The universe continues to expand, and the pace of expansion varies based on the observed location. The cosmic microwave background, CMB, is the residual thermal radiation originating from the primordial event known as the Big Bang. The cosmic microwave background, CMB, is not observable to the naked eye, although it pervades the whole universe. Humans cannot perceive it because of its low temperature, only 2.725 degrees above absolute zero, 459.67 degrees Fahrenheit, or 273.15 degrees Celsius. Consequently, the radiation it emits is predominantly detectable in the microwave region of the electromagnetic spectrum. As per NASA, the cosmic microwave background, CMB, is present throughout the cosmos. In the era before cable television, any household with a television could observe the residual radiation from the Big Bang. You can observe the cosmic microwave background, CMB, as a stationary signal on the screen by tuning the television to an intermediate channel. How did the cosmic microwave background form? We can trace the universe's origin to approximately 13.8 billion years ago, and the cosmic microwave background, CMB, emerged approximately 400,000 years after the Big Bang. During the early phases of the universe, when it was only 100 millionth of its current size, its temperature was extremely high, measuring 273 million degrees above absolute zero, according to NASA. Subatomic particles, specifically protons and electrons, quickly detach from any existing atoms. The electrons deflected the photons emanating from the cosmic microwave background, CMB. According to NASA, photons travelled through the early universe in a manner similar to how optical light moves through a thick fog, NASA stated. Approximately 380,000 years following the Big Bang, the universe's temperature had decreased sufficiently for hydrogen to begin to take shape. Hydrogen minimally impacts the cosmic microwave background, CMB photons, resulting in their propagation along linear paths. Cosmologists use the term surface of last scattering to describe the point in the universe's history when it became too large. When we observe the cosmic microwave background (CMB, we essentially study the cosmos at a point in time approximately 380,000 years after the Big Bang. This is the period when the universe became opaque to radiation. Robert Wilson and Arno Penzias identified cosmic microwave background (CMB) radiation in 1964, providing strong evidence for the validity of the Big Bang theory. In recognition of their discovery, Wilson and Penzias received the 1978 Nobel Prize in Physics. They jointly received the medal alongside Soviet scientist Pyotr Kapitsa. In 1948, Ralph Afer, an American cosmologist, predicted the cosmic microwave background, CMB, while collaborating with Robert Herman and George Gamow, as stated by NASA. The team's research focused on Big Bang nucleosynthesis, which refers to the formation of elements in the cosmos beyond the lightest isotope of hydrogen. Nevertheless, detecting the cosmic microwave background, CMB, was serendipitous. In 1965, Arno Penzias and Robert Wilson, researchers at Bell Telephone Laboratories, encountered an enigmatic noise while developing a radio receiver. They quickly recognized that the sound originated uniformly from several locations in the sky. Simultaneously, a research group at Princeton University, under the leadership of Robert Dicke, was endeavoring to detect the cosmic microwave background, CMB. Following their study of the Bell experiment, Dicke's research team verified the existence of the cosmic microwave background, CMB. Both teams rapidly published in the Astrophysical Journal in 1965. Penzias and Wilson presented their observations while Dicke's group explained the implications within the framework of the cosmos. In 1978, Penzias and Wilson received the Nobel Prize in Physics. The cosmic microwave background provides valuable insights. The cosmic microwave background, CMB, is a valuable tool for comprehending the genesis of the early universe. Highly accurate telescopes can observe the consistent temperature with few variations. By examining these variations, cosmologists can gain knowledge about the genesis of galaxies and the extensive arrangements of galaxies, while also quantifying the fundamental parameters of the Big Bang theory, NASA stated. NASA launched the Cosmic Background Explorer, COBE, project in 1989 and concluded scientific operations in 1993. This project generated the first comprehensive picture of the entire sky from orbit, providing a detailed representation of the cosmic microwave background, CMB, several years after its initial detection. NASA characterizes this as an infantile depiction of the cosmos, validating predictions of the Big Bang theory and unveiling previously unnoticed indications of cosmic organization. The COBE project earned John Mather, a scientist at the NASA Goddard Space Flight Center, and George Smoot, a scientist at the University of California, Berkeley, the Nobel Prize in Physics in 2006. The Wilkinson Microwave Anisotropy Probe, WMAP, a satellite launched in June 2001 and ceased gathering scientific data in 2010, provided a more comprehensive map in 2003. The initial image estimated the universe's age to be 13.7 billion years, later revised to 13.8 billion years. Also, it unveiled an unexpected finding. The earliest stars began emitting light approximately 200 million years after the Big Bang, significantly earlier than anticipated. We must address novel inquiries arising from the cosmic microwave background, CMB radiation, which provides insights into the age and composition of the universe. Investigate the mechanisms that underlie the detection of the cosmic microwave background at this location. After these discoveries, researchers investigated the initial inflationary phases of the universe, occurring within the trillionth second after its birth, and yielded more accurate measurements of atom density, the unevenness of the universe, and other characteristics shortly after its inception. In addition, they observed an anomalous imbalance in the average temperatures in both hemispheres of the sky, as well as a cold spot of greater magnitude than anticipated. The WMAP team received the 2018 Breakthrough Prize in Fundamental Physics for their research. In 2013, the European Space Agency's Planck Space Telescope published data that unveiled the most accurate depiction of the cosmic microwave background, CMB, until that point. When they received this data, scientists discovered an additional puzzle. The fluctuations in the cosmic microwave background, CMB, at significant angular scales did not align with the anticipated predictions. Planck also validated WMAP's observations on the asymmetry and cold spot. The 2018 data release from the Planck mission, active from 2009 to 2013, provided further evidence supporting the existence of dark matter and dark energy. These enigmatic forces are believed responsible for the universe's accelerated expansion. Other research endeavours have examined various facets of the cosmic microwave background, CMB. One aspect involves identifying the different forms of polarization, including the E modes, first observed by the Degree Angular Scale Interferometer in Antarctica in 2002, and B modes. The gravitational lensing of E modes, first detected by the South Pole Telescope in 2013, and gravitational waves, first discovered by the Advanced Laser Interferometer Gravitational Wave Observatory, (LIGO), in 2016, can generate B modes. In 2014, the BICEP-2 sensor in Antarctica announced the discovery of B modes in gravitational waves. However, Planck's research and further investigation revealed that cosmic dust was the cause of these findings. Scientists are currently searching for the signal indicating a transient phase of rapid cosmic expansion that occurred immediately after the Big Bang, as of mid-2018. During that period, the expansion rate of the cosmos surpassed that of light. Scientists predict that this event may be detectable in the cosmic microwave background, CMB, through polarization if it occurs. In that particular year, a study proposed that nanodiamonds emit a subtle yet detectable glow that hampers cosmic investigations. According to the study authors, having considered this luminous effect, future investigations can now eliminate it to more accurately see the subtle polarization in the CMB. The primordial cosmos was characterized by harsh conditions. Dense packing of energy and matter resulted in an unimaginably small and extremely hot environment, 1 billion times hotter than the Sun. Following the Big Bang, the temperature of the cosmos decreased sufficiently for the emergence of elementary particles, including quarks and electrons. Quarks amalgamate to form protons and neutrons, swiftly followed by deuterium, helium, and lithium nuclei production. At every instance, photons, the energy particles that sped across the early universe, bounced off unattached electrons that had not yet attached to any atom. After approximately an additional 380,000 years, the temperature of the cosmos had decreased sufficiently for the early nuclei to attract electrons and combine to form neutral atoms. We use the term recombination to describe this process despite the fact that it signifies the first occurrence of these particles merging. This moment marked the beginning of an era characterized by the absence of light, now commonly known as the cosmic dark ages. The retina or a camera can detect photons, which is necessary for object observation through human vision or a telescope. A dense cloud of neutral hydrogen enveloped the universe during the cosmic dark ages, preventing the light from the earliest stars and galaxies from escaping. The cloud cleared just 1 billion years after the Big Bang, when the neutral hydrogen underwent reionization and separated once more. During the Dark Ages, light could not exit its immediate environment, preventing it from propagating through the universe and reaching our detectors on Earth, a distance of roughly 13 billion years. Attempting to reminisce about that period feels akin to perceiving a light bulb through a dense, obscure mist. However, interesting things were happening below the surface, even though we couldn't see them. Consider the Dark Ages on Earth, which occurred between 500 and 1000 AD. 500 and 1000. Even though it doesn't look like a time of big cultural or scientific growth, there were forces at work that would later set off the Renaissance. Similarly, the cosmic Dark Ages brought about significant changes that left a puzzle to solve. Avi Loeb, an astronomer at the Harvard-Smithsonian Center for Astrophysics and one of the first to study this early universe period, states, "This period is not just a transition, it's a transformation. It's the point where the universe went from being simple to complex." They got a good picture of how things were at the time. The first neutral atoms formed, sending light photons across the universe. Along the way, they took a picture of the exact conditions at the start of their journey. This old cosmic microwave background, CMB, radiation surrounds us. It shows that the universe's mass wasn't too different at the time, with only small changes. The cosmic microwave background, CMB radiation, has waves that don't seem important, but they are actually the beginnings of the universe's change. Avi Loeb, an astronomer at the Harvard-Smithsonian Center for Astrophysics, says these changes create things like galaxies when put into a computer program. The Dark Ages were the most important time in the history of the universe's development, from these small changes to objects, galaxies, and stars. This is a huge shift in the story of the universe. We still need to learn more about the exact steps involved in this change. Astronomers are sure about one thing. Why can't we see any light from things shining in the Dark Ages? Before the first stars formed, there wasn't much light. The majority of the universe is composed of dark matter, which doesn't give off light. Also, a cosmic fog of neutral hydrogen atoms covered the universe and scattered or absorbed many of the ultraviolet UV rays that the first stars sent out. The time it would take for a photon to escape the hydrogen was longer than the universe's age, says Professor Bahram Mobasher of Physics and Astronomy at the University of California, Riverside. We observed that these galaxies ionized the atoms around them, resulting in ionized hydrogen bubbles that overlapped. See inset for an illustration of this effect. Astronomers believe that as more galaxies formed, these bubbles got bigger and bigger until they merged all over the universe, ending the Dark Ages. Things improved after the Dark Ages. A few 100 million years after the Big Bang, when matter started to stick together and form the structures that make up the universe today, the first stars and galaxies began to form. This is similar to how the universe became clear to ultraviolet light again. Some light. Some of the first stars were big and bright. Their light was strong enough to ionize the hydrogen atoms around them, which means it took the electrons out of the atoms. Ionized hydrogen also doesn't absorb or spread light like neutral hydrogen does. The first stars and galaxies formed, and their light brought the universe out of the Dark Ages, he says. As new stars and galaxies formed, they ionized bubbles that continued to grow around them. This allows light to move freely again. Astronomers cannot see the cosmic Dark Ages, but can see the light from these early galaxies as the darkness ends. Along with people from other countries, Mobasher and his team looked at some of the farthest galaxies ever reported. We look for galaxies at the end of the Dark Ages, he says. That is the farthest thing we can find in the universe. Mobasher and his colleagues used information from the Cosmic Deep and Wide Narrowband, or Cosmic Dawn survey, to publish a paper in the astrophysical journal Letters in February 2020. The paper described a group of galaxies ionizing the hydrogen around them about 680 million years after the Big Bang. People who study the Big Bang believe that the age of ionization occurred between a few 100 million and 1 billion years ago. By studying this cosmic dawn, Mobasher hopes to find answers to some of the most important questions we have about the universe. He believes understanding the Dark Ages will help us understand how galaxies form, stars form, and galaxies move across the universe. We need to find out important things like how our galaxy began, how it formed, and how fast it added stars. Don't forget that hydrogen atoms wouldn't have soaked up all the light in the very early universe. Certain wavelengths of light are the only ones that a hydrogen atom can receive because they have the right amount of energy for its electron to move from one energy level to the next. Therefore, new instruments such as the James Webb Space Telescope, the Hydrogen Epoch of Ionization Array in South Africa, and the Square Kilometre Array in Australia and South Africa are beginning to function. These will help us find this light. The universe is growing, which makes light stretch out over time. This is why we need these infrared and radio telescopes. The first stars emitted light in the far ultraviolet spectrum. This light has a much longer wavelength now than it did back then. With these new tools, we'll learn more about the epoch of reionization, which is the start of the cosmic dawn. Loeb hopes that these detectors will help him figure out the big puzzles of that time. We will be able to see the history of things that took place during reionization, he adds. What you need to know about the cosmic dark ages is that the first hydrogen atoms in the universe absorbed light from the first stars, he says. As time passed, the universe grew bigger with more stars and galaxies, which turned this hydrogen back into ions. This allows photons to move easily in all directions. The movie, The Universe. Dark Ages shows how the universe changes over time. It starts with many galaxies in the present day and ends with just one orange point. What are the dark times of space? The term cosmic dark ages describes a period in the early universe when a dense fog of neutral hydrogen gas obscured light sources. Light can now move through the universe in all directions, making it clear. However, in the beginning, hydrogen covered the universe, absorbing the light from the first stars and other radiation sources. For the first 380,000 years after the Big Bang, everything in the universe was a hot, dense, glowing ball of ionized plasma. Subatomic particles in this high-energy soup were crashing into each other at this point, stopping them from getting electrons and forming stable atoms. But after the universe had cooled down and spread enough, subatomic particles could pick up electrons to turn into neutral hydrogen atoms. This was the start of the cosmic dark ages. But after enough stars formed, their ultraviolet light eventually ionized all the hydrogen in the space between the stars. This lets neutral hydrogen not absorb or scatter photons, allowing them to move freely through the universe. Physicists think the cosmic dark ages started about 380,000 years after the Big Bang. This information is derived from simulations and observations. Scientists believe the events that ended the cosmic dark ages started about 680 million years after the Big Bang and concluded about 1.1 billion years later. Most scientists concur that the formation of the first neutral hydrogen atoms 380,000 years after the Big Bang marked the beginning of the cosmic dark ages. However, no one agrees exactly when the dark ages ended. Reionization happens when big early stars in the universe send ultraviolet light into space. This process probably took a few million years, during which time more and more stars came into being. Early observations of galaxies show that ionization began about 680 million years after the Big Bang. The visible universe likely reached full ionization about 1.1 billion years later. What brought an end to the cosmic dark ages? It took a long time for the cosmic dark ages to end. In the early universe, areas with more neutral hydrogen gas finally collapsed under their own weight to form massive stars, the first stars in the universe. Many ultraviolet rays came from these stars and into the nearby universe, but it wasn't until there were a lot of stars and protogalaxies in the early universe that enough ultraviolet light reached space to ionize all the neutral hydrogen in the space between the stars. When hydrogen first appeared in the universe, it began the cosmic dark ages. During the Big Bang, it was very hot. But as the universe grew, there was enough room for the dense plasma of protons, electrons, and other subatomic particles to cool. This lets the electrons and protons unite to make atoms, mostly hydrogen and a small amount of helium. Even though the galactic abundance of hydrogen finally gave rise to the first galaxies and stars, the early universe was hard to see because the primordial hydrogen absorbed different types of light across the electromagnetic spectrum. But as the first galaxies and stars spread out across the universe, they sent out enough photons, high-energy ultraviolet radiation, into the area between the stars to remove the electrons from neutral hydrogen atoms. These hydrogen atoms with electrons did not absorb these high-energy photons. Instead, they let them move across the universe over very long distances. According to astronomers, the first galaxies and the universe are thought to have had their first stars and galaxies around 500 million years ago. These early stellar populations spread the first heavy elements across the universe and started the reionization process, which made it possible for light to move through space without any problems. Astronomers can now see these patterns in the early universe like never before, thanks to the near-infrared camera on the James Webb Space Telescope. It has revealed some surprising things. Studies of these early galaxies have shown that they are much brighter than galaxy formation models had expected. One possible theory is that these early galaxies were full of hot stars. Going back into the dark ages of the cosmic ring, there are two clear things that make it hard for us to observe the universe as it was during the cosmic dark ages. For starters, the time was very dark because thick clouds of hydrogen blocked light sources. However, cosmologists and scientists believe that one day we might be able to see radio waves from hydrogen gas that originated during this time in the early universe. The Earth's atmosphere prevents strong radio waves from reaching us. Only from space can we see them. One day, though, a telescope on the moon might be able to see back to a time when the universe looked very different from how it does now. Scientists have demonstrated that a radio telescope on the moon could provide insights into the cosmic dark ages. The formation of stars has always captivated both scientists and the general public. The dirty, often beautiful, molecular star-forming Earth and the solar system, which formed 4.6 billion years ago, hide important parts of our history, so we must learn more about this event. Astronomers study the births of other stars and stellar systems in stellar maternity wards nearby. They use these as a time machine to see how our solar system came to be. Some of Hubble's most beautiful pictures also show places where stars are being born. The Orion Nebula is a part of the Milky Way, where new stars are being born. Hubble images have revealed proplyds, dust circles surrounding newly formed stars, initially believed to be planetary systems. A large mosaic of 15 Hubble images captures the heart of the Orion cluster, providing one of the most detailed images ever captured of a star-forming region. The picture shows a young star cluster releasing a bubble from its parent cloud of burning gas. This lets the visible light of the stars shine through, like how heat pushes smoke away from a forest fire. Hubble's sharp images have helped us learn much about the proplyds and dust rings around the new stars in the Orion Nebula. There is a good chance that the proplyds are young planetary systems just starting to form. More than the details that instruments on the ground could show, Hubble has shown that dusty disks around young stars are widespread. It seems that starbirth always occurs in dusty places, which is why Hubble's infrared skills have been useful. Dust clouds often block infrared light, making infrared studies the only means to observe young stars. Improvements made to Hubble during its 2009 servicing mission have made it an excellent camera for studying infrared light. We designed the Wide Field Camera 3 WFC3 instrument to capture detailed images in both visible light and infrared. Its infrared skills are much better than they were before the servicing mission. The Carina Nebula looks like thick clouds of dust and gas in visible light from WFC3. But when the camera takes pictures of the same area in infrared, the dust fades, leaving only a weak outline of where it was. The sudden light indicates that young stars are forming inside the cloud. The dust clouds look nice, but they get in the way of what scientists want to see for the most part. How stars are made and how the universe has changed over time. Able 383, a group of galaxies, is a gravitational lens. This process, which bends and boosts the light from faraway galaxies, allows astronomers to study star formation in galaxies that would be too far away and faint to see. Hubble has also contributed to understanding how stars form in galaxies other than the Milky Way. The Hubble or any other camera can't see each star outside the Milky Way. The same goes for a few nearby galaxies in the so-called local group. On the other hand, the telescope has helped scientists make important findings about how stars form in the farthest reaches of the universe. Because their light must travel such vast distances to reach us, it allows us to see galaxies that were once far away. Hubble has seen light from very far away, and things tell us about how stars formed in the universe's early days and how they have changed over time. This is not the same as the beautiful Hubble pictures we save to our screens. These objects may be too far away or small to see clearly, appearing only as dots or small blobs in the pictures. Even though they don't look very interesting, that doesn't mean they are hard to study. Scientists can figure out a lot about things that give off light, even if they can't see them clearly, using methods like spectroscopy, which breaks light into its individual colours. Hubble and ground-based telescopes work together in this important area. Hubble takes detailed pictures of objects that help us figure out where they are in the sky, but big telescopes on the ground are often better placed to study their spectra. Gravitational lensing is another tool that astronomers use. This is when the gravity of a group of galaxies between us and the object being studied turns light beams toward us. In early universe star formation, Hubble made important discoveries such as realizing that galaxies and stars formed earlier than thought. Hubble has had a major impact in two areas of star formation. First, it studied how stars like our Sun form and saw what may become planetary systems around those stars. Second, Hubble has affected what you might call cosmological star formation, which is the process by which stars are made all over the universe. For example, the door opened with Hubble Deep Field North, and we could see how stars formed across the universe. This lets us study the cosmic evolution of the stars. Over the past few years, we've learned that hundreds of stars have planets circling them. Stars are huge, bright spheres of plasma. The Milky Way galaxy has billions of them, including our own Sun.